drawn in the other blackboard, all these ones, they they do not have any ADS in their geometry, right? So when you look at the metric nowhere looks like ADS. So you are breaking conformality. That's what produces this flow, this normalization group flow, and the presence of these scales, right? So you are breaking conformality, you are inducing scales. You are breaking, in that particular case, to half of the supersymmetries, still far away from what you may consider phenomenologically interesting, but we are going to patch this in a second. And remember that all these metrics, they had a factor, something, and some sphere, right? So there will be an isometry. Okay, let me see if I'm writing this right. So for yes, is this correct? Yes, right. Yeah. Okay. So I'm in this particular example, I'm kind of conserving not the SO6, but the SO large global symmetry or R symmetry. But I'm certainly touching the conformality, and I'm certainly touching the supersymmetries. Okay, so that's just the feature of this particular example. But I was I was stopping in this particular example because I think it's a nice way of seeing this flow in degrees of freedom, and it's a nice way of convincing yourself that this radial coordinate is an energy coordinate, right? And how whenever you expect a description to be good, that description is good, and whenever you expect that description to be bad, that description is bad. By good and bad, I mean perturbative or non-perturbative. So the topic of this hour is, okay, let's take this idea seriously, and let's try to construct models. By the way, this we said is for DP brains, so the theories are either in 0 plus 1, 1 plus 1, 2 plus 1 dimensions, or 4 plus 1, 5 plus 1, 6 plus 1 dimensions. So let's take this kind of ideas seriously, and let's try to go over things that people have done to construct models dual to field theories in 4 dimensions with no or minimal supersymmetry and with interesting dynamics. Okay, so that will be the outcome of today's and probably one of the tomorrow's lectures. So let me go over that. So we'll now fix our attention, and this is, by the way, you will see as I go talking about this, you will see how generalizable is the thing that I will say, but I will focus the attention, just for the sake of being concrete and not confusing, to examples, duals to 3 plus 1 dimensional quantum field theories with minimal or no supersymmetry. And again, what I'm going to say, you will immediately appreciate. It can be generalized to higher amounts of supersymmetry, different dimensions, etc., etc. But let's. So the idea is now using these objects, these brains, right, to construct a configuration of brains, if you want. Let me call it a configuration of brains. To construct a configuration of brains, okay? Or what I should say, string background, supergravity background, such that it can be argued to be dual to a field theory that will contain certainly the gauge field, certainly fermion, maybe or maybe not scalars, will live in 3 plus 1 dimensions and will be minimally supersymmetric or non-supersymmetric. Okay? So people have taken this project seriously, and there are actually different ways, different things you can do. I'll try today at least to explain these different ways, at least conceptually and with some calculation. And and tomorrow I'll go into some particular technicality of this or that, and why it's interesting, and etc. etc. So, what would you like? Okay, if one were to choose what you want, you would like a field theory. I'm going now to draw an energy scale. I'm going now to draw a radius scale. In this correspondence that we are discussing, radius on the string side is kind of an energy scale on the field theory side. So it's going to be a quantum field theoretical description and string theory description. And so what would you want is that, and now we are focusing on the case of 3 + 1 dimensions, right? So if you want by the book, if we have to go by the book, what we would like is to start with a conformal theory, okay? We would like to start with a CFT at a conformal fixed point at very high energies, right? Think about QCD, right? That tends to be conformal, very high energies. And then deform this theory at different scales. No relations to the lambda 1, lambda 2 I was discussing before. Different scales. How would you deform the theory? Well, look, you can do different things. Either impose that some operator of this theory is getting a verb, or introduce the form de Lagrangian, but some other operator. Typically a marginal or a relevant operator, such that it will take over your infrared dynamics. Right? Let me say it again, because I think I'm not saying this clearly. If you were to be as Wilsonian as you can be, you would start from a conformal fixed point, weakly or strongly coupled. Okay? You would deform this conformal fixed point, and you would flow into a theory of our interest, right? A theory that confines, if there is chiral symmetry, breaks it, different phenomenology. It may have a Goldstone or not, etc., etc. So how you go about it? Well, you start with your conformal theory at very high energies, but actually your theory has different scales at which you are either giving verbs to operators or inserting operators, again, typically marginal or relevant. You don't want to insert an irrelevant because it will take off your conformality. Same here. Same here. Okay? And your wish would be to end up with some non-supersymmetric or minimally supersymmetric Young-Mills-like theory.
Yeah, I have one stupid thing to ask actually. If you start off with a CFT and you deform by a marginal operator, would you not always end up with a CFT as well?
No, if your operator is marginal, you will go to a CFT.
Yeah.
Right? But suppose that you deform with a marginal but also give a verb, right?
Okay,
so the dynamics is more complicated.
Okay, so both of them.
Yes, both things, or even more, just deform with a relevant.
Yeah,
right?
sure.
And that's
but I'm saying if you're just deforming
if you are
with
exactly
the
marginal,
operator,
you will flow to another CFT.
You flow to another CFT, right?
And by the way, there are many examples of those, right? So we can discuss examples if needed, but there are many examples where you start with some CFT,
and you flow to another.
you go with a marginal, you flow to another CFT with different characteristics. Typically, this one less symmetric under different global symmetry, supersymmetries than this one.
Okay.
Many examples of these are very well understood. And what's interesting about these examples is that since you give a string description of this, you are deforming with an operator that is exactly marginal even at strong coupling, right? That's what makes it interesting, right? So in field theory, it's difficult to know that an operator is marginal because how do you know if you go higher order that it will not become dangerously irrelevant, that is dangerously irrelevant? You don't know, right? So this perspective gives you that.
Another naive question at your endpoint, of course, is not lambda equals 0. This is
some other scale.
Some other scale.
Yeah. Let me say it in this way. Suppose that this is your confinement scale, right? Good. So, suppose, just for the sake of the argument, that this conformal theory is our n equals 4 superior limits. Just, and this is just for the argument. This will change. This can change in a moment. Then what you would impose on your background is that, okay, look, far away in the radial coordinate, the metric will look like ADS phi crosses phi, because you know that this is how the duality works. Okay? But remember that in ADS phi crosses phi, you are turning on only in this particular solution, as we discussed, a metric and a phi form field strength. Okay? So suppose actually that what you do is to construct a metric that, okay, at leading order in a large row asymptotics, at leading order in a large row expansion, only these two fields survive and are not zero. But it happens that if you start coming with that expansion towards your infrared, towards your smaller row, well, then at some point some fields start to get a value. Okay? This become non-zero. And by the way, I'm doing this in type 2b, but a very similar picture can be developed in type 2a. Okay, so what there will be is a change in this metric. Let me call it a flow in the language that we were developing in the previous hour. And you will flow into some interesting, or not, metric or background, let me say. Okay, some more complicated background. So your proposal will be that infrared aspects of this full field theory will be captured somewhat by this more interesting background. And if you want, this full background will capture the full flow that is going on here. That will be the proposal. Okay? The tricky point here is actually to find this, right? To find this background doing this trick. Okay? So people have developed lots of interesting ways to go about finding these kind of things. Right? So let me give you, just to fix the idea, one example that is an example that I particularly dislike, but let me give it in any case, because it's very clean. And then I can tell you why I particularly dislike it. There is nothing wrong with it, but it's not nice, but you will see. I'm going to write a metric. I'm going to write a phi form. And I'm going to write the dilaton, whose functional form I'm going to specify. Okay, so let me first tell you what this sigma 4 is. Depending on this value here of alpha, If alpha is 0, that sigma 4 is just Minkowski space. If alpha is -1, or if alpha is +1, this sigma 4 is either anti de Sitter 4, or this sigma 4 is just de Sitter 4. Okay, so believe me the following statement that I'm going to make. This thing is a solution to the equations of motion of type 2b string theory. Of type 2b supergravity, let me say. This is a solution that preserves 0 supersymmetries. And now let me think it in the following way. What I'm going to say, it will either resonate immediately with you or produce no change in your knowledge, right? So, but for those with which this will resonate, let me say, if you take C equals 0, take C, this number equals 0, okay? This is just a way of writing this dr squared 1 plus alpha e to the minus 2r, and this thing is just a way of writing anti de Sitter 5 as a foliation with Minkowski, anti de Sitter 4 or de Sitter 4, okay? Those of you who know cosmology, you know that there are these ways of writing when they write the Friedman-Robertson-Walker. In the three-dimensional part, they can write flat, hyperbolic, or a spherical. And this is very much the same. This is just a way of writing anti de Sitter 5. If this were 0, this is a way of writing anti de Sitter 5 with a flat, hyperbolic, or spherical foliation. Okay? But the thing ceases to be anti de Sitter whenever this one is there. Okay? So you see what's happening here. If you go to very large values of this radial coordinate, for r going to infinity, well, look, it's not much of a mistake to say this term is almost not there, right? So ignore this one. Oh, and your thing now is ADS. It's ADS 5 cross whatever 5 manifold, okay? But as long as you are coming to smaller and smaller, and by the way, and the dilaton notice, okay, is going to be really very suppressed, right? As a function of r. So it's going to be really a constant as a function of r. But notice that as you are coming to smaller and smaller values of the radial coordinate, this will start to wane. This will start to take a functional form. This will basically stay the same. So okay, this will make not much of a mess. So you may want to think that what you are doing is deforming this n equals 4 by the addition of some belt, because it's something that takes your infrared. Yeah? And you are deforming it in such a way that it's a non-supersymmetric deformation, and is basically realizing this flow in a very simple example. Okay? So the only reason why I'm mentioning this is because it realizes this thing in a very 3 lines example, and if you believe that that's a solution, then you can see how the thing is done. Is this clear? Yes? Can you see this flow in here, right? So that's why it's very illustrative as an example. Is this clear to especially the young people in the audience? Jamie, this good? Johan? Yeah. I always ask my favorite swanses, right? So the rest I don't care. Okay, good. So this is just an example of these flows. I can tell you later why.
One small thing again. So I mean, if we are looking at some general flow in this case, I mean, how do we? I mean, how does one make sure that the things that you get at the end of the day do preserve Einstein's equation and things like that?
You will impose that whatever is the solution is solving the Einstein's equations. Okay. So look here, this one, believe me, solves the Einstein's equations of type 2b, right? So it's really quick to check. So you will restrict yourself in this case to just solve Einstein's equations in such a way that somewhat I'm turning on some field so that while starting at an ADS point, and turning on some field that will deform the ADS, will deform those original symmetries into something else. Okay? Tell me again your question.
I'm trying to say go from ADS5 cross S5, deform it by some operators, and what do I need to impose to get something at the end of the day which is going to preserve Einstein's equations? I mean,
say it this way.
Yeah.
In this perspective, don't say deform it but some operators. Say we will turn on other
these
fields.
yes.
Right?
Yes.
Turn on other fields.
Yes.
But we'll still turn them on
Yeah.
in such a way that the Einstein's equations
Are-
are Dilaton
yeah.
equation, everything is preserved,
Yeah.
is solved, right?
So I mean, so we get the thing at the end of the day, and I mean check that if it preserves Einstein's equations and the rest of.
I would check it at the beginning of the day. If it doesn't preserve, don't even. You are looking for solutions,
Yes.
right?
Yes.
Such that asymptote to ADS5,
Yes.
right?
Right.
So it may happen that these solutions are singular in the infrared. It may happen. It may not happen. This one is not. Right? This one is healthy in all respects. It may happen that those solutions preserve or not some amount of supersymmetry.
Yeah.
This one does not.
Yeah.
Okay. But all along the flow, you are solving Einstein's equations. You propose, if you want, think it in this way. Let's propose this solution. Okay, so we will propose some. So how we go about this? So we propose. We want something that is related to ADS5, and for some reason we decide to pick this example. Right?
Yes.
So we will propose some metric with some function there that I don't know, some radial coordinate,
Yes.
right, that I don't know, and for some reason we'll become inspired and we'll pick a phi sphere with some function that we don't know.
Sure.
And we'll propose that the dilaton is some function that we don't know of that radial coordinate, but we'll still keep the phi of the form volume of this and volume of that.
And
Right?
then we choose f and g and things so that our equations are preserved.
Exactly. So then we write the equations of motion of
Yeah.
this and say, let's solve it, right?
Sure.
And it's characteristically it's a mess, right?
Yeah.
Because the equations are non-linear. There is one problem that we would like to back up from. Let's make everything depending only on R, so they
Yeah.
will be at least ordinary equations,
Yeah.
right? But they will be non-linear for certain, and they
Yeah.
will be coupled.
Yes.
So in principle, it's a mess. In this example, you just do a couple of tricks and you bring it into one equation that you solve, and you see you don't solve it so nicely because something you have to leave it as an integral, but okay.
Yeah.
All right, so that's a solution. But this is the way you go about, right? So you propose something, impose the equations of motion on it, gives you equations, gives you solutions. If you are lucky, you find the solution in this way. If you are unlucky, you find it in either series expansion, numerical interpolation, right? There is all the art that people have developed. Is this clear? Luigi?
So if I understand you correctly, as long as c is equal to 0, this is just a rewriting of ADS.
Yes, yes,
Right, so it
yes.
remains conform
Yeah, indeed.
with all scales.
Indeed.
So really it's c that breaks.
Exactly.
the
Yeah, yeah.
Is there a direct identification between the parameters in the
Yes,
metric
yes,
and the
yes.
verbs?
Yes. You can see that this C is the strength with which you are inserting a verb for some operator. Right? This you can see there is a very well defined dictionary between deformations you do to ADS, right, and operators, dimensions of operators in the field theory. In this case, you can see by this deformation. This I studied very long ago, in 2003, so I will not remember it from the top of my mind. But if you study how this deformation goes, this is called, by the way, holographic renormalization group. So when you study that, you can check which is the dimension of the operator that you are inserting, right? And with which strength. And the strength is also is that number C. As you said, you switch it off and the thing disappears. Okay.
Is this something you can glean from this description of group circular and Polyakov and
Yeah, exactly. So this
gives you
is exactly. Yeah. So in this gap circular of Polyakov thing, what you would be saying, if you were to catch this metric, is a step forward the gap search framework probably could think. So if you were to catch, they proposed something for ADS5 spaces, right? But okay, it was in 1998. So then many people, most notably Skenderis and people around him, developed a way of computing correlation functions and learning about what these kind of deformations are, if they are BEVs, if they are insertions of operators, etc. In geometries that are only asymptotically ADS. Okay? And what's interesting is that this asymptotically works not only for UV asymptotical ADS, but also for infrared asymptotical ADS. So you can have a theory where you are putting some irrelevant operator in your infrared will be conformal, and then your ultraviolet will be a horrible disaster, but you can read how you are deforming that infrared conformal theory using that. So what we did back in 2003 with Dan Friedman, Martin Schnabel, and Kostas Skenderis with this thing was to prove that in spite of being non-supersymmetric, is stable, right? All the formations you may want to do of this thing still keep this solution as solution of less energy than whatever is the deformation. Okay? But then people kept on using this kind of techniques and etc. Is a nice thing, but
So you mean stable in the gravitational sense?
Yeah. Because you have a non-supersymmetric solution, and the first thing that people will ask you is, I do a perturbation, will be stable, and in this case it is. So some of you may have heard about this. This is what started a line that people now call fake supergravity, etc. Let me not go over that. So coming back to Arshon's question, the thing that you will be imposing is always to propose something that solves the Einstein's and Dilaton and Maxwell's equations for the fields and Bianchi identities for the fields, etc., etc. And if you are lucky, and if not, you should distrust the thing you are getting, not because it's wrong, because your approximation is breaking down, you should get a solution that is free of any singularity or things like those, right? So you see, if for example, somewhere here, your dilaton, somewhere in this solution, your dilaton were to blow, you should be worried about that and say, look, that's where my approximation is breaking down, this solution, I should not study there. If somewhere here your Ricci scalar were to blow, well, you should not really go into that region. You should suppose that the Ricci scalar were to blow here. So you should not trust whatever this interesting metric is telling you about this Yang-Mills-like theory, because you're out of your approximation. Okay? So all the examples I will be talking about are examples where these bad things do not occur. Okay? So they are all completely singularity-free metrics, and everything is trustable, and etc. All right, this is just one example of those. Good.
So why don't you like the example?
Sorry? Oh, because the dual field theory is a very ugly one because of the following. When you study this and alpha is -1, suppose that alpha is 0, right? So this is not here. So how was the thing? Okay, this presents a singularity. If alpha is 1, same. But if alpha is -1, this space will end before r equals, so the radial coordinate here could go from +∞ to -∞. -∞ would be your infrared, +∞ your ultraviolet. If alpha is either 1 or 0, you will hit a singularity. But if alpha is -1, there is a moment where this vanishes, and it vanishes in a smooth way. So there is no singularity. But that is making your field theory to live in a space that is not your usual 4-dimensional space, but has kind of a wedge. Right? So this is what we studied in that paper. Right? So I always found this completely unappealing. But I don't know if people like it. Okay. So I never work on this again, but that's just personal. And it's not wrong, it's just what it is, right? In this particular example. Okay. So
Could you just give us
tell me.
1 minute of why it's a field theory in a wedge?
Yeah. So you see that I was drawing this. So if alpha is -1,
Yeah.
so your space is complete when R goes from plus infinity to minus infinity. Right here you are cutting your space, so suddenly the space is closing.
Okay.
It's kind of it's conical. So whenever you put a vortex in 2+1 space, this vortex will eat up part of your space. Right. So it's kind of something like this. Right. So you can see that your metric, okay, is theoretically complete, all the nice things, but your space has a deficit
Yes.
angle, to say that way. Okay. Forgot a lot about these details. When I was young, I could have explained you this from the top of my mind. I forgot. And probably I forgot it just to defend psychologically myself against that exam. Okay, so let me give another example. Okay, now let me tell you, while this is a generic idea and it's the same idea of the flows in the DP brains, etc., this is the idea you would like to go with. Let me say something about this approximation we are discussing, and then let me classify the different ways people have gone over applying this idea, and tomorrow we discuss some technical subtleties about one or the other. First, let me say something. So let me plot actually the Toft coupling in terms of the energy. Right? For field theories like this, for field theories like this one that I'm talking about here. But let me emphasize that let me plot what we would like to have. So what we would like to have is to have a quantum field theory where there is one scale, let me call it the Lambda-Young-Mills, the confinement scale, if you want. And so this is this field theory, by the way, this is this one. And then separate enough from this Lambda-Young-Mills scale, these other extra scales, right? Let me call them Lambda-UV. Why you would like this? Well, because you would have a long range where the field theory, or your dual description to a field theory, is a dual description to a field theory you consider interesting, say this one, Young-Mills, right? So the theory to compare with the lattice people. That will be your goal in the best scenario. So notice two things. Here we are giving a gravity background that we would like to be dual to field theory like this. What you get whenever you write a gravity background is something like this. Now I'll try to be. This is what you get, actually. So let me make 2 points. The first one is that if your field theory is asymptotically something, if your gravity solution is asymptotically ADS phi crosses phi, and this S phi, and this ADS has a radius that, remember, we associated with the square root of the Toft coupling, and the Toft coupling is large, the radius of the space is large, so the Toft coupling will never be asymptotically free, okay? Right, so you will not, in the gravity approximation, get asymptotically free theories, okay? Right, so that's one point to be said. You will get in the gravity approximation asymptotically strongly coupled theories. So your field theory will be strongly coupled all over the place, okay? So this conformal point will be strongly coupled, unlike the one in quantum chromodynamics. This is clear as a first point, right? This is a first proviso to be made here. The second is that whenever you work in this supergravity approximation, this you can see is a not long calculation and is qualitatively valid in all the examples I'm going to mention. This completion is almost degenerate with the scale you would like to study. So you will never be studying your interesting Young-Mills theory, but you will always be studying your Young-Mills theory, if you want, with contaminations from this ultraviolet completion. Okay? The attitude I take to this is the following. Look, I'm not interested in Young-Mills, I'm interested in this field theory. Right? And this is the theory that I want to study, and I cannot separate in this approximation these scales. Never mind, I'll study this theory.
What is the parameter on the gravity side that separates the two?
Right. So the parameter is okay. There will be various parameters here, but the parameter is again related to this Ricci scale. Right. Whenever the gravity solution is trustable, I mean, whenever the theory is strongly coupled, to say it in other words, whenever the gravity solution is trustable, you will be in a situation, and again I can convince you with a short calculation about this, you will be in a situation where your UV completion will kick almost at the same scale as your interesting scale. Okay? So, okay, it is what it is. This is if you work in the gravity approximation. If you decide to improve on your gravity approximation by adding to your Lagrangian terms that go like this, etc., well, you will be able to relax this condition, but you will pay in solving equations that are more complicated. Okay, so it's a compromise of what you want to do. The parameter that is controlling the thing is this alpha prime parameter that you take to 0 to avoid seeing, this is the string tension, you take to 0 to avoid seeing these things. They come weighted like this, etc., etc. You take to 0 to avoid seeing them, but then it hits you back in this way. Okay? So either you find a solution where you are including all these corrections, that would mean to work with the sigma model for those stringly initiated, or you decide to live with this limitation and you go with it. All right? So this is qualitatively a limitation that will apply to all the cases that I will mention now. All right? Good. So now let me tell you the different ways in which people have gone over this idea, making it concrete in different examples. So what I will give now is just a classification, and for each one of these classifications there are different examples that people have worked out explicitly, and tomorrow I'll try to mention some of the technicalities, some characteristic technicalities to all of them. So the first one is just start from ABS phi cross phi. The form in this way we are discussing, and flow into some metric. Okay? And then propose that this some metric, this full metric, is dual to this full field theory with all its deformations, etc. You will read with techniques that people have developed. There are many examples of this, most notably examples by Italians, non-Italians, and really lots of examples, right? On this, in this sense, Pilch, Warner, etc. The thing is, the thing that distinguishes these examples, if you want, these examples are very initial, right? They happen around the year 2000. So in those examples, it happens that they are finding a metric doing precisely this thing very nicely, but then is singular here, right? So you should not trust very much whatever you may learn about this. But as examples, they were very illuminating because they were indicating very clearly a road to be followed. Okay. Clevenon, and a very distinguished list of collaborators, starting with Witter, Nekrasov, Zeitlin, in different papers. Strassler, and recently Dimarsky, Cyber, etc. Many students of Klebanov also have developed a line where this conformal field theory is not n equals 4. It's not n equals 4. So you start from an n equals 1 conformal field theory. It's a particular field theory. We can discuss bits about it tomorrow. It's what people call equivalent field theory. So it's a field theory with two gauge groups and matter transforming in the fundamental of one gauge group and the anti-fundamental of the other, or as people call it, bifundamentals. The two gauge groups need not to have the same rank, but if you want to be a conformal theory, they must have the same rank. And what they do is a deformation, that in this case the deformation is to unbalance, disbalance these ranks. And there is a flow in this field theory, a flow that field theoretically can be understood quite well into a field theory, and tomorrow I can discuss this, into an SUM field theory, supersymmetric, with some Goldstone multiplet. So there is one massless particle here. So all this flow is minimally supersymmetric. All this flow is field theoretically quite well understood. And what happens on this side is that if you are starting from a conformal field theory, you better have an ADS5. Right? The ADS5 contains the symmetries of a conformal theory, but the fact that the conformal theory is not n equals 4, but it's n equals 1, well, basically at this level just changes your external space. It's no longer a phi sphere, is what's called a coniform. If you're not familiar with this, just take the word for it. We can discuss tomorrow what's this thing. So there is a metric and a phi form, and this deformation basically turns on this Ramon-3 form and this Neveu-Schwarz-3 form. And the dilaton, unlike the example I was mentioning, keeps on being constant in here. So you flow into some interesting solution that is free of any singularity, is completely trustable, and this is a very conceptually very powerful example because, and I can discuss some of these things tomorrow, many field theoretical aspects here can be very cleanly seen how they are encoded in this method. Right? Many non-perturbative field theoretical aspects can be very cleanly seen encoded in this method. There is another approach that again follows very much this line with a small subtlety, that is taking higher dimensional branes, so D4s, D5s, D6. So as we discussed before, the solutions for these higher dimensional branes is known. They preserve a large amount of supersymmetry. They have a large amount of global symmetry. Right? So what you do here is to change this solution in the following way. You have a higher dimensional brane where a p plus 1 field theory lives. Just let's take an example. Let's take p equals 4. Right? So this is a set of 4 branes. There is a 5-dimensional field theory living here. And what you will do is you will catch one direction and you will make it compact. Okay? In the case of 4 branes, for the case p equals 4, you will catch one direction and you put it in a circle. In a case p equals 5, you will catch 2 directions and you will put them on sphere. In a case p equals 3, you will have p equals 6, you will have three directions you will put it on a 3 sphere, or any other compact manifold will do. The thing is that it's difficult to find solutions. And so the idea here is the following. if you look at this system now, and by the way, you will find a new solution doing this, and I will just mention it in a second. If you look at this kind of solutions, and you explore them with very long wavelengths at very low energies, right, with very long wavelengths, what you will be seeing is a 3+1 dimensional theory, right? So your physics will happen in 3+1 dimensions. The moment you start exploring it at higher energies, with very small wavelengths at high frequencies, your modes will be able to enter into your extra dimensional space. And if you want, if you were to have an accelerator and you were able to tune the energy, this is what you would see. This would be your weakly coupled spectrum. So you would see a gauge field, perhaps a fermion, if the thing is supersymmetric, no fermion, if the thing is non-supersymmetric. Then you will have a gap. Again, this is the weakly coupled spectrum. You will have a gap. The gap will be related to the size of these extra dimensions. Okay? You will have a gap, and you will start seeing whatever comes from the Kaluza-Klein reduction of the higher dimensional field theory. So you will start seeing massive gauge fields, massive scalars, massive fermions, not necessarily the jelly. It will depend on how this compactification goes. And like this, a tower, right? As it happens in any Kaluza-Klein example. Okay? The thing is that in doing this kind of reduction, you will do it in a tricky way, such that you will either break the full supersymmetry and break at least part of this global symmetry into something that is more affine to us, more akin to us. So these examples will typically preserve no supersymmetry or minimal supersymmetry. And you can see how these examples are very flexible in the sense of generalizing them, right? So you could have taken 4 branes and put them on a 2-manifold, making a dual to a 2+1 field theory with no supersymmetry, minimal supersymmetry. It's all a technicality for how to go over different examples, and people have exploited that technicality a lot. But I hope that is clear that this example is conceptually different from this and this and this, in the sense that the ultraviolet completion, right, at very high energies, the theory is not necessarily a conformal theory in 4 dimensions, but a higher dimensional field theory. Okay, so you will, it's clear, right? So what you see is a Kaluza-Klein structure. So what you will be dealing with is a theory that at low energies it will be your favorite Young-Mills-like theory. As soon as you start pumping up the energy, you will start seeing lots of other states. You will recognize this as a higher dimensional field theory. It's a different beast. Okay, so it's a nice way of studying infrareds, right? Well, the ultraviolets, one will have to wave your hands or whatever it is what the thing will be. So people have written backgrounds describing this situation, and all the others I was mentioning. And just for illustrative purposes and to finish with this, let me write the background in this particular example. Let me put it here. So in that particular example, you are taking NCD4 branes. You are compactifying them in a circle. And you are going to do it in a tricky way, and the trick is the following. You see, when you compactify things, typically you do not break supersymmetry. You will do it, in this case, you will do this compactification by imposing periodic boundary conditions for the bosons and anti-periodic boundary conditions for the fermions. Okay, so that will break supersymmetry for you.
Isn't that like finite temperature?
Very good. It's like finite temperature, and you will see the metric now, and you will recognize the black hole in here, but you will recognize the trick of it. Okay, it is like finite temperature, but you will see what I will write now. So for those of you who don't know this technical subtlety, every time you do like what's called the Matsubara decomposition in a finite temperature field theory, you do this kind of trick. You impose some boundary conditions for bosons, some boundary conditions for fermions, and and what you have to do is periodic and anti-periodic for one or the other. So that's how you go in finite temperature. So that's what Jose is saying. Isn't this like finite temperature? I'm saying yes. And you should associate finite temperature with the presence of black holes, right? You will see what will happen here. So the metric is very much black hole-ish, but with a very interesting. So let me copy things properly. There is a factor. So these are your 4 dimensions of where your field theory will be living. This is kind of a 5th dimension, the one that you are compactifying here. I'm calling it phi. So you have a 4 sphere, a radial direction, 5 directions, that counts up to 10, and this work factor, that is one, is the inverse of the other. And notice that this is the inverse of this. This work factor is and this function is given by this. Lambda is a number, R is a number. Okay? So the point that you are making is isn't this like finite temperature? In other words, isn't this like a black hole, right? And you can see where the black hole is, right? The black hole is kind of here, right? So this is the typical structure of a black hole, right? And this is the typical function that will give you horizon, right? So what's happening here, this metric was constructed by considering a black hole and then making a double Wick rotation, where they were compactifying time, they were making time into I phi, etc. So that's why this was, in the original situation, this was your time, and this was your black hole. But you see here, this is a very simple metric. Notice, by the way, that this radial coordinate rho will take values between the value lambda and infinity. Okay? So the minimal radial value you can get is when this vanishes, right? And the space stops there. There is no below that. And just let me comment about something we discussed yesterday, and with this we finish.
So sorry, Carlos,
Yeah.
One question. So H again, there could be a constant that you
Exactly.
dropped.
Yeah. And actually, H is actually okay. This is the inverse of H. Right, something like this. I'm dropping this constant. I'm going to the near horizon in the discussion of the previous hour, etc., etc. And what I'm writing here is the h to the minus a half or h to the plus a half, etc. Correct? So indeed there is an integration constant that I'm taking out from the game in order to decouple the field theory from gravity, in order to work with the field theory itself. So this is a metric. There is, by the way, a Ramond 4 form that, just let me say, is proportional to the volume of that 4 sphere, and there is a dilaton here that is basically this function h. Up to some power, but kind of irrelevant here. Yeah. So I was going to say something. Remember that yesterday we were discussing in the computation of the Wilson loop in a generic case, etc., and we got a formula for a generic metric. Sorry, let me say this better. For a generic metric with a GTT component, a GXX component, and a GRR component, we define a couple of functions. We call them f squared and g squared. This was GTT times g radial. This was GTT times GXX. And I was saying that we were able to write an expression for the energy between the quark and the anti-quark pair Right? So we have this quark and anti-quark external sources. We are computing the Wilson loop, and we were writing this energy in terms of the distance separation between the pair. There was a coefficient here where this function f was appearing at the end of the space, remember? And then corrections, subleading corrections. Subleading in L. Subleading in LQQ. So notice that, for example, in this example, it's quite simple to see that the function f, or f squared, that is gtt times gxx, is h squared. So it's h squared, so it's this, right? When you evaluate this at the end of the space, that is not rho equals 0, but rho equals lambda, right? It gives you a constant. And this constant is the QCD string tension in this example. So this example will give you a confining behavior, okay? Is this clear? Right? So the only reason why I developed all this story yesterday was just to check in these examples, whenever I write their metrics, that this quantity is there, is non-zero, and this typically gives you an area law, right? For the. So what this would be telling you is that this field theory that you obtain by taking these four branes, compactifying them on a circle, breaking all the supersymmetries, and this weakly coupled field theory with a gauge field, and then massive gauge fields, fermions and bosons, massive with the different masses and different degeneracies, etc. This field theory, if you were to introduce two very heavy probes and compute the potential between these probes, it will show you something that up to some UV behavior then will become linear and will confine as it should happen in any Young-Mills-like theory. Okay? So let's cut this here because people look more tired than necessary. So tomorrow I will try to discuss and I'll try to avoid horrible technicalities. This Klebanov system and just a bit of this minimally supersymmetric system in order to make some connection with what lattice people here might be interested, this walking story I've been working on, etc. I'll comment something on that, okay? So, thanks very much.